Method development for synchronizing processor time of accelerometer with computer for sensor-equipped health measurements. By Marcus Holzschuher, Rebecca Heinz, Joseph Russell, Maria Lissner, Jeroen Bergman, and Anja Winkler. Read by Joseph Russell. Presented on the 14th of July 2025 at the Annual International Conference of the IEEE Engineering in Medicine and Biology Society, EMBC. Abstract. This paper presents a method for the precise synchronization of inertial measurement unit, IMU data, with a computer system clock, using a motor-controlled turntable to allow more accurate labeling of motion data. Using the case of human reaction time measurement, where motion is recorded as a response to a computer-controlled visual signal, this methodology proved capable of compensating for IMU clock drift and latency between systems, providing a robust and simple solution for applications in a wide range of IMU sensor-equipped systems. Clinical relevance. This approach addresses time discrepancies that compromise data quality, enhancing the reliability of motion analysis in biomedical applications. 1. Introduction. The synchronization of IMU data plays a crucial role in the accuracy of motion data collected through sensor-equipped systems. To analyze motion data captured by IMUs in response to a computer-generated signal event, as in the case of measuring human reaction times, it is crucial to align the recorded datasets. While many IMU manufacturers enable easy synchronization of clocks between IMUs and other platform-level systems, direct synchronization with a computer processor clock remains challenging. This paper presents a method for synchronizing IMU datasets clock with computer processor clock, using an Arduino-controlled rotating turntable as a trigger synchronization instrument. 2. Methods. The experiment employed two XSense IMUs, XSense 1, mounted on a turntable for synchronization, and XSense 2, measuring participant reaction time, as shown in Figure 1. Both were synchronized to a shared clock, recording data at 60 Hz. The turntable was driven by an Arduino-controlled direct current motor, generating a reproducible motion pattern. The reaction time was determined based on 10 trials. The participant performed a targeted hand movement while holding the XSense 2 in response to a computer-generated visual signal. This signal was displayed as a number in the Python console. XSense 2 recorded motion changes as timestamps within the dataset. Reaction time was calculated as the difference between these timestamps and those of the visual signal, after aligning the motion data to the computer processor clock. To evaluate the effectiveness of the synchronization method, the mean reaction times were measured for both the synchronized and unsynchronized motion data, and compared to a ground truth reaction time. The ground truth was obtained through video analysis at 240 frames per second by counting the frames between the visual signal and the participant's motion response. Figure 1. Schematic overview of the synchronization system setup. To achieve precise synchronization of motion data, a two-stage trigger process was implemented. Communication between the Arduino and the computer via the serial monitor, which is a built-in interface for data exchange, enabled this synchronization. Before and after the reaction time measurements with XSense 2, 3 synchronization tests were conducted, during which the computer initiated the rotation of the turntable by sending a command to the Arduino. The timestamps of the turntable's rotation initiation, logged via the serial monitor, were compared with motion changes detected by the XSense 1 sensor. The discrepancies between these timestamps provided the temporal offset between the IMU clock and the computer processor clock. Repeating the synchronization at the beginning and end of the experiment addressed clock drift in the IMUs. 3. Results and discussion. The ground truth reaction time was measured at 420.416 milliseconds, plus minus 201.147 milliseconds, while the reaction times for the synchronized and unsynchronized systems were determined to be 432.830 milliseconds, plus minus 235.385 milliseconds, and 287.226 milliseconds, plus minus 234.668 milliseconds, respectively. The mean error, when compared to the ground truth, was reduced by approximately 36% in the synchronized system. Specifically, the mean error in the synchronized setup was measured at 84.922 milliseconds, plus minus 96.800 milliseconds, while the unsynchronized system exhibited a notably higher mean error of 133.191 milliseconds, plus minus 127.354 milliseconds. These results demonstrate that the proposed synchronization method effectively minimized time discrepancies between the IMU clocks and the computer processor clock. This research was supported by the BBSRC, grant number UKRI 012. Funding Trans-Campus Initiative, TU Dresden and King's College London. Joseph Russell, University of Oxford. Conference costs supported by prosthesis.